So I'm Robert Winglee. I'm in the Department of Earth and Space Sciences here at the University of Washington, and I'm also, in my spare time, the director of the Washington NASA Space Grant Consortium, which serves undergraduate students across Washington State, as well as the director of NASA's Northwest Earth and Space Sciences Pipeline, serving middle school and high school students also across the Northwest. Beth asked me to, again, strongly focus on the ripple effect for JCATI. And so what I'd like to say is that it really has been an important nexus that has enabled us to collaborate between the NASA resources that we have in JCATI to really bring technology to the students across Washington and across the US. We started actually in our laboratory devices in 2014 with a plasma thruster. So plasma thruster is something that uses high voltage to break down material to produce a very energetic exhaust plume, which is at higher speeds than you could get from chemical systems. It was a laboratory device, and so we went to JCATI, and actually, so that's a picture there of the plasma thruster actually in operation. Plasma thruster is a little bit unique compared to those other systems in that it's pulsed, which means that I can vary the amount of energy density, so I can actually break down any kind of material that you would like to break down and make it into a plasma and eject it out for the system. And so it could either be for a low power system and just have a long duty cycle, or have a very high power system with a very short duty cycle. And then in 2001 with JCATI, they enabled us to go from a laboratory device to start playing around with a system that could be spacecraft ready. So we had some very rudimentary designs for a CubeSat, so that's a 3U version of it, but it was fairly rudimentary with it. But with the JCATI resources, we were able to actually formalize it and become competitive as we move forward from a laboratory device to a spacecraft device. And so they gave us some additional funding in 2016 to make a full version towards a pulse plasma system for small satellites and maybe even upper atmospheric UAVs. And so that was where the JCATI funding came in. So it provided a catalyst for our students, and you can see that we went from this 3D printed version to this version here, which is a flight stack, which will be delivered to NASA in September for launch up to the space station. So we are able to go from laboratory in 2014 to flight in 5 years. And we're mainly done with students. And so what with JCATI helped us to do is leverage those resources. So with the start from JCATI, we were able to successfully compete with NASA's undergraduate student instrument program, and they gave us another $200,000, I should say, to help make it into a flight-ready system. Although I was just working with the people at NASA to get us through all the paperwork, and there was a discrepancy in one of the numbers, and I said, well, that was because we were working with undergraduates, and the guy said, working with undergraduates, oh no. But nevertheless, I told them that this was an undergraduate program and it was important for our effort. And then talking about leverage, you saw that, you know what the JCATI provides us, but then we got the launch. We're going up on the NanoRack system on a Cygnus capsule, as I mentioned, and later this year. And those launch costs are about $300,000. So you can already see that there is massive leveraging from what JCATI was able to provide us, and we wouldn't have been competitive without the JCATI support. Beth also asked us then to talk about, unanticipated results. So one of the things we found is that we could break down just about anything we wanted to. You saw the Back to the Future where he throws the banana peel into his device. Well, we've thrown dirt into our plasma thruster, and we can ionize that as well. So we're having science reproduce fiction. But one of the things that we did come up, so that was moving towards in situ resource utilization, but maybe a little bit too far out in the future. But we did discover that we could actually make a really efficient device that could work at 100,000 feet. And so that was a serendipitous discovery that moved us in towards other opportunities. So we actually flew a modified device that we're using on our CubeSat to make a high-altitude flyer that we've been demonstrating with. We started in 2017, where we've been able to take up our high-altitude flyer. I call it a flyer because it's actually lifted up by a balloon. So basically, instead of having a runway down here and having to try and get the flyer to work through the atmosphere, we've actually lifted it up to 100,000 feet on a balloon. And we have a little camera. Those flashes there on the right are actually part of the plasma thruster going, and it's pulse, so you don't get a full image of it. And then, more importantly, we're able to actually bring it down successfully in one piece. And so the figures on the right there are us landing in a field in eastern Washington. Also unanticipated results is that on one of the flights, the payload was actually eaten by a cow. Who knew? We are playing around. We are collaborating now with Eagle Harbour Technology to see whether we could use the system for a hypersonic re-entry system, where in fact you're using the neutrals at very low density up there to be able to convert it into thrust. And so instead of trying to take off from below, we're actually trying to fly from above and down towards. And so that has applications in not only our Earth's atmosphere, but any planet with an atmosphere or solar system object with an atmosphere. So that's an unanticipated result, but I wanted to say that it's not just about hardware, it's also about our students that participate. And I know that, we've got a lot of academics here, and, maybe the industry guys are saying, oh, what does it do for us? But nevertheless, we have had, this is our little baby group in 2016, and then we've grown substantially to 2018. We've had over 100 students participate in the CubeSat development over the years, and you can see that we have provided bodies to a lot of the aerospace companies here in Washington, including Aerojet, Blue Origin, Boeing, Microsoft, Planetary Resources, Google, Northrop, and some of the other Californians ones, which we won't mention, okay? But we've also provided some to the NASA centers as well, because these guys have got substantial hands-on experience. And I was mentioning to one of the other talkers here is I also get them to learn how to do all the paperwork, because I refuse to do the paperwork. But that's something that industry really wants. And so these guys are really coming up really highly qualified as they move forward. We also send them out to graduate school, and a lot of them have gone to fairly prestigious schools here, including UW. I was going to make another comment about the fact that we don't have other universities in Washington here, but nevertheless, we have a good, strong commitment to making these students move forward in their academic facilities as next career steps. And another serendipitous effort was that there were a couple of companies that needed promotional work. But the promotional work is all, intellectually property protected, and they didn't want their stuff getting out into the big bad world because they're trying to be competitive. But they know us academics are always blurting stuff out in public about what our material needs to be. So we helped Sigma Design, for example. They did vibe tests for us for free, but we're allowed to demonstrate our results as part of their PR effort. And similarly, Delphine Precision Imaging, they wanted something to CAT scan that we could show what their devices could do without providing trade secrets away. So they actually scanned our sulfur-Duran plasma thruster to look at the porosity of the system. So again, it's a good way of actually expanding the impact that JCATI has been able to let us do. So just summarising then, to me, the JCATI has been very essential for us to create a seed program to allow us to be more effective in the federal grants that are moving out to it. Because without that footprint, in the space sciences or space technology, everybody's looking that you have to have heritage on your device. And it's like catch-22. If you don't have heritage, then you don't get funded. But if you don't have funding, you can never get heritage. So JCATI gave us that step up, and we really appreciate that effort. We've been able to, as we said, establish new innovations across the area, different applications. And again, the student outcomes to me, since I'm here at the University of Washington, find it very important. And I think that has been something that I really highly value. So thank you.